Today in Math 30-1, we're looking at topic 8.1, Understanding Logarithms. First of all, from our exponential functions, we know that y equals c to the power of x. The inverse function would be x equals c to the power of y. As I said, that's our exponential function. X equals c to the power of y is our logarithmic function. This is written as y equals log base c of x, where c is any positive number other than 1. Since our number system is base 10, logs with base 10 are called common logs. Base 10 logs don't need their base when you're written. For instance, when you see log 6, that means log base 10 of 6. In example 1a, log base 7 of 49. And since 7 squared is 49, the log base 7 of 49 would equal 2. Log base 6 of 1, well, 6 to the power of 0 is equal to 1. So log base 6 of 1 is 0. For c, the log of 0.001, well, we're going to take 10 to the power negative 3 is equal to 0.001. That means that the log of 0.001 has to be negative 3. And for d, the log base 2 of root 8. Well, the log, we can say that 2 to what power is root 8? Well, we're going to express root 8 as 2 to the power of 3 underneath the root sign. Now we can say that that's going to be to the power of a half. So 2 to the power of x would be 2 to the power of 3 times a half, which is 3 over 2. Now we can say that x must equal 3 over 2. Here's some restrictions, or identities. Log base c of 1 is equal to 0 because c to the power of 0 is equal to 1. Log base c of c equals 1 because c to the power of 1 is going to equal c. Next, log base c of c to the power of x is just going to be x because c to the power of x, of course, is equal to c to the power of x. And lastly, c to the power of log c of x is equal to x, and x cannot equal 0 because the log c of x is equal to the log base c of x. These last two are called inverse properties. And example 2 asks us to determine the value of x. In A, log base 5 of x is equal to negative 3. Well, that means that we're going to write that as 5 to the power of negative 3 is going to be equals to x. And that's got to be 1 over 5 cubed, which is 1 over 125. In B, we have log base x of 36 is equal to 2. So that must mean that x to the power of 2 is equal to 36. So x is equal to the square root of 36, which is positive or negative 6. But remember that c has to be any positive number. So c has to be greater than 0. Positive 6 is our only acceptable solution. Part C. The log base 64 of x is equal to 2/3. So what we're going to write is that 64 to the power of 2/3 is equal to x. Now we're going to say that's the same as the cubed root of 64 squared is equal to x. The cubed root of 64 is 4, so 4 squared is x, and x will equal 16. In this example 3, we're going to graph the inverse of an exponential function. And A, state the inverse of f at x equals 3 to the power of x and sketch both graphs. Well, first of all, let's come up with a list of ordered pairs of 3 to the power of x. We know that 3 to the power of negative 3 is going to be 1 over 3 to the power of 3, which is 1 over 27. The next one, 3 to the power of negative 2, is going to be 1 over 3 to the power of 2, which is 1 over 9. Next one's 1 over 3, and then 1, 3, 9, and 27. Now the inverse function is the log base 3 of x. And when you write the inverse, the x and y values get interchanged. So the x value is going to be 1 over 27, and the y value will become negative 3. Again, next one, the x value will be 1 over 9, and the y value will be negative 2. And on down the line. So when we graph these two functions, they're going to be inverses of each other. And what is that going to look like? Well, the first graph is in blue, the second graph is in red. And what we have is looks like a reflection over the axis, not the axis, but the line of y equals x that goes through the middle of those two. So notice that the graph of the inverse function, which is in red, f inverse of x is log 3 of x, is a reflection of the graph y equals 3 to the power of x about the line y equals x. Now we're going to ask for certain characteristics of this graph, these two graphs, the domain, the range, the x-intercept, the y-intercept, and the equation of the asymptotes. In our original function, we're going to say that for the domain, x is going to be any real number. For the range, y has got to be greater than 0, but not equal to 0. The x-intercept, there isn't going to be one. The y-intercept is going to be at 1, and there's one of them. And the equation of the asymptote, you can see as you approach 0, so it's going to be at y equals 0. Now if we compare that to the other one, starting backwards, the equation of the asymptote is now x equals 0. How many y-intercepts are there? None. The x-intercept is going to be at 1. Now we can say that the domain and range, well, the domain is going to be x has to be greater than 0, and the y has got to be the domain. That means that the y is going to be any real number. Therefore, let's keep going. Example 4. Estimate the value of a log without technology and find the value of log base 2 of 14 to 1 decimal place. Without technology, we mean without using any of the log functions. So the log base 2 of 14 we'd like to find. We know that 2 to the power of 3 is 8. And we know that 2 to the power 2 to the power 4 is 16. One's too high, one's too low. We want to get to the log base 2 of 14, so it's going to be closer to 4 than 3. So let's try 3.7. So 2 to the power 3.7 is approximately equal to 13, which is again a little bit low. Let's try 3.8. And then 2 to the power of 3.8 is equal to approximately 14. So within 1 decimal place, we can say that log base 2 of 14 is equal to 3.8. In your turn, find the log base 3 of 50 to 1 decimal place. So here we're going to say 3 to the power of x is 50. 3 to the power of 3 is 27. 3 to the power of 4 is 81. Go halfway, 3 to the power of 5. 3 to the power of 3.5 is about 47. And 3 to the power of 3.6 is about 52. So 3 to the power of 6 is closer. We can say that the log base 3 of 50 is approximately 3.6. Here we have an application of logarithms. Earthquake magnitude is measured on a Richter scale. M is equal to the log of A divided by A to sub-zero, where amplitude of the ground motion, usually in microns, divided by the amplitude corrected for distance to actual earthquake that would be expected for a standard earthquake. In an earthquake struck Vancouver in 1946. It had an amplitude that was 10 to the power of 7.3 times A. What was the magnitude on the Richter scale? We can say that M is equal to the log of A divided by A0, and replace A with 10 to the power of 7.3 A0. Now we have M is equal to the log of 10 to the power of 7.3 A0 over A0. We can cancel the A0s, and we got M is equal to the log of 10 to the power of 7.3. That is 7.3. B. The strongest earthquake to hit Canada was 8.1. How many times as great as A0 was its magnitude? Well, we use the formula again, except this time we're going to take out the M and put in 8.1, because that's the magnitude. Now what we're going to do is we're going to say that we're going to take out the log and say that 10 to the power of 8.1 is A divided by A over 0. Multiply both sides by A to the 0, and you're going to find that A is going to equal 10 to the power of 8.1 times the expected standard earthquake. And that is going to be 125,892,541 times the expected standard earthquake. Therefore, it's almost 126 million times as great as a standard earthquake. C. Compare the two earthquakes. Well, we have an earthquake of 8.1 and an earthquake of 7.3. So I can say 10.81 A0 over 10.7, 10 to the power of 7.3 A0. Cancel the A0s, and you're left with 10 to the power of 8.1 over 10 to the power of 7.3, and using your calculator, you can find that that's going to equal 6.3. That means that an earthquake of magnitude 8.1 is 6.3 times as great as an earthquake of magnitude 7.3. Your assignment, page 380, numbers 1 to 20.